This video will give a brief overview of an ANOVA, an analysis of variance. In the past, we have worked with comparing the means of two populations, but very often we want to compare the means among multiple populations. So for example, let's take a look at our classes. Suppose I have 4 sections of Stat 2, and I have a sample of final exam scores from each of those 4 sections. An analysis of variance allows us to compare the mean of those final exam scores among the 4 sections. And we can ask the question, do the samples provide sufficient evidence to conclude there is a difference in final exam scores among 4 different sections of Stat 2? These different sections are called our factors. Or, sorry, you will see them called in this textbook treatments. Essentially, what we are looking for our test statistic, you will see, is one simple formula. We are using an F-test statistic, which we'll go over in a minute. And what we have is the treatment mean squares divided by the error mean squares. So essentially, what does that mean? The treatment mean squares will look at the variation that is occurring among all our 4 groups, where the error mean square will look at the variation that's occurring within each group itself. Clearly, as we progress, you will start to notice if there is more variation among the groups than there is within the groups, we will have a much larger test statistic, causing us to reject our null hypothesis, which is going to state there is no difference among those groups. What I want to focus on right now is understanding some of the terminology and some of the notation that you're going to use when doing analysis of variance. So I want you to real quick kind of take a look at your formula sheet. And let's go over some of this notation so we have a better idea. You see over here, here's your test statistic. Now, you will also, as you work backwards, find that there's a lot of computations to get to the MSTR and the MSE. But we'll get there in a minute. Don't worry about that. So here's some notation that's given on your formula sheet. K represents the number of populations. So in our formula, our K is 4, because we have 4 populations. And we will number them. I conveniently numbered them for you. 1, 2, 3, 4. So if you take a look, N is the total number of observations. So notice that this N does not have any subscript, where N sub j does have a subscript. When there's no subscript, then that N is referring to the total of all of them. So we have 4 here. 1, 2, 3, 4, 5, 3, and 4. So the N without a subscript is going to be 16, where N sub 1 is 4, N sub 2 is 5, N sub 3 is 3, and N sub 4 equals 4. Please pay attention to this as you're going through the problems. The same is going to be for, notice you have an X bar without a subscript. That's going to represent the mean of the entire set of data, where each individual X bar with subscripts is going to represent the mean of each population. Same for variance. So I do want to go over, sorry about that, moved away, this idea of the mean for a second. One second. Erase this. So what you are given in this particular problem is your actual data. As you know, we work with data and we work with summary statistics. So if I want to convert this to summary statistics, I would then need, hold on, there you go, to find the mean of each data set. I've already done that for you. You guys can utilize your calculators for this, or you can plug the numbers into StatCrunch and quickly get summary statistics from either StatCrunch or your graphing calculator if you have one. If not, you'll have to just calculate the mean by hand. So I have 74.5. The mean of the second set of data is 75.4. The mean of the third set of data came out to 81. And the mean of the fourth set of data came out to 71. Now, I do want to quickly review, because this particular formula is not on your formula sheet, how do we find the mean of the entire set of data without using all the individual numbers? Because there are going to be problems where you're going to be given that summary statistics and not the original data. So in other words, if I have 4 groups with 4 different means, and each group is a different size, how do I find the total mean of the entire sample of data? So let's go over that real quick. So this one, of course, is 3, and this one. It's going to depend on the sample size. So when you cannot just add up the 4 means and divide by 4 because they're weighted differently because they have a different, the sample sizes are different sizes. So to find a total mean, let's go to section 1. There are 4 samples, and our mean is 74.5. For section 2, I have 5 pieces of data, and my mean is 75.4. For section 3, I have 3 pieces of data. My mean is 81. And for section 4, I have 4 pieces of data, and the mean is 71. You will add all those numbers up. That actually will give you the total, the same total if you were to add every single one of the 16 values up. And because we have 16 numbers, we're going to divide by 16. So let's go ahead and do that. And I got a total of 1202 divided by our total sample size of 16 to get an X bar of 75.125. So we will need to work with the different means as we go through this, so I just wanted to make sure you knew how to do that. Now let's talk degrees of freedom for a second. Your degree of freedom formula, of course, can be found on your formula sheet. You will see that it looks like k minus 1 comma n minus k. The first number for the degrees of freedom will always represent the degrees of freedom of the numerator, and the second number, the n minus k, is going to represent degrees of freedom of the denominator. So for this particular problem, if you recall, our k is 4 because we have 4 populations. So our degrees of freedom here is going to be 3. 4 minus 1 is 3. And then we had 16 total minus that 4, 12. So when we look at our chart, we're looking at 3, 12. So let's go to our F table for a second. And you will notice your F table has degrees of freedom of the denominator down the first column and degrees of freedom of the numerator across the top. So, if you recall, our numerator was a 3 and our denominator was a 12. So when you go to your F table, you go across to 3 and go down. You have a second table next to it on your formula sheet. So go 3, 12. This is the box of numbers we will be looking at dependent upon what our significance level is. Okay, so let's try some practice problems just looking at how to use the table. And let's talk about just the F distribution itself for a minute. You will notice it looks very much like our chi-square distribution. It starts at 0, just like the chi-square, and it is right skewed like the chi-square. The total area will always equal 1, just like all the other curves we have worked with, and is right skewed. So let's try some examples. First thing I want to do is, if we were doing a problem using a critical value approach, we have to find critical values. So the first critical value I want you to find on your table is f of 0.10 with degrees of freedom 412. So go to your f table. We want 412. It's this box of numbers. You can hit pause at any time to find it on your own first. And I had stated we wanted 0.10 for a significance level. So 0.10, your critical value in that case is going to be 2.48. So if I was drawing an F curve, my critical value would be 2.48, and if my F's test statistic falls on this side, it's reject, and over here would be do not reject. So now I want you to try it at a 0.05 significance level with degrees of freedom 3, 5. So 3, 5 at 0.05 appears to be 5.41 for the second one. This would be 5.41, and this is 2.48. And of course, the other thing we have to do with our F tables when we're evaluating our hypothesis is a p-value approach. So let's take a look at that one. For the first problem, I want you to look at, if we got a test statistic of 4.87 and our degrees of freedom were 211, what would that p-value be? So in this problem, of course, it's your test stat that goes here, and your p-value is going to represent this area. Well, just like with the t-table, we're not going to get an exact answer, but we can approximate it. Let's look at 211 on our table. Two for the numerator, go down to 11. I'm looking at this box of numbers, and I want you to find where 4.87 is going to fall in that box. Well, 4.87 is clearly between these two values, 3.98 and 5.20. So that means your p-value is between, always put the smaller one first, 0.025 and 0.05. So you can estimate your p-value between 0.025 and 0.05, and that should be enough information to make the determination to reject or not reject based on the significance level of whatever alpha is for the particular problem you're working with. So let's try one more. We have a test statistic of 17.89. Degrees of freedom 4.5. Go to your table. We have degrees of freedom 4.5, so that's 4. Let's go down to degrees. Denominator is 5. This block of data, and our test stat was 17, which is clearly larger than the largest number in this block of information. So that means if you take a look, notice your areas are going down. So if your test stat is larger than the largest number in your group, that means your p-value is smaller than that smallest area. And in that case, we would have a p-value that is smaller than 0.005. And then again, you would look at your significance level, but this p-value is so small, you would clearly be rejecting.